For the 6th exercise session of CASS, we will be repeating everything we've learned so far from session 1 until 5. So the goal of session 6 is not to teach you any new concepts, but to give you some more practice in everything we've already seen. We're doing this by creating a big exercise about linked lists, which you will have to implement. Now, first of all, let me say this exercise is not meant to be completable within a single exercise session. You will have 2.5 hours time in the session to ask questions, to get started, but in the end, it will probably take a lot more time than that. There is of course no obligation for you to complete this exercise, but the goal of the session for us is to provide the students with enough material so that they can practice programming in RISC-V. And the idea is, if you can complete this full exercise, you should be well prepared for the programming part of the exam. By practicing, you will go a lot faster, you will need less time at the exam, you can spend more time on other questions, and practicing simply by programming is, in my opinion, the best way to get to know the concepts. So for this exercise session, you just need to get as far as you can, basically. Ask questions when you're stuck. And what we will be doing in the exercise is implementing a linked list data structure with multiple methods, both in C and in RISC-V. Now again, on the exam, you will only be evaluated on the RISC-V part. But chances are quite high that you will get C code, which you will need to translate to RISC-V. So to translate C code, it's a good idea to be able to write the C code, because then you understand what happens. I'm not saying it's impossible to simply translate without having ever written a line of C, but it's probably not the best idea. So what this session will be is you will be implementing methods of a linked list data structure, first in C, and then you will translate your own implementation to RISC-V. My suggestion would be to do this method by method. So for example, we will have a list create function, translate it, write it in C first, and then immediately translate it to RISC-V and switch between the two. I think personally that will be the best way to solve this exercise, but it's all up to you. If you want to do the C part completely first and translate afterwards, that's fine as well. Doing the RISC-V part first is also possible, but it's a strange order to take. Let's now give you a quick recap about linked lists and dynamic memory. And also, the only thing we actually have to explain here is how C deals with dynamic memory. We haven't explicitly treated this yet in session 4, and you will need this for the implementation in C. So let's jump into the presentation. Let's think again about how dynamic memory worked. We had our heap memory here. This is a visual representation, or this is a representation of the heap. Let's say when you start your program, it contains a bunch of random data, or maybe all zeros in this case. That's not a guarantee, but let's assume for now. But all of this, it's grayed out because it's not initialized. This is just some random space in memory. And we're going to create a dynamic data structure here. I'm going to use the example of a stack, which is the one you implemented in, I think, the 3rd exercise of session 4. So what would happen if we could create a stack? Then we would reserve, this is how we did it in session 4. We reserve space here. We reserve 1 word of space to store a pointer. And this will be the pointer to our stack. We have on the right column here, we're going to have a visual representation of the stack. And currently this is empty. So what we have done is we've created a pointer, a stack top pointer, which is uninitialized. It's pointing to 0, meaning that it's pointing to nowhere. And that's our representation of an empty stack. Basically, a pointer stored somewhere in dynamic memory, which is pointing to 0. If we would, what's stored in S here, this would be the address of this pointer. So in this case, this pointer is actually at address 0 if we consider this to be the first address in memory. But yeah, this block of memory could be anywhere in memory, of course. Let's now see what happens when we push an element to the stack. So let's look at the visual representation. First, we've pushed the value 5 to the stack S. So what happened here? The stack pointer moved. It's pointing now somewhere else. And we have here an element added, which is the value 5. So this is obviously a stack with one element, and the stack top is pointing to this one element. How is this represented in memory? What changed? Well, now our first stack top pointer here is not pointing to the value 0 anymore, denoting that it's pointing to nowhere. It's pointing to the first element. And we've considered this to be address 1 here. So we are pointing basically to this square with the 5. This pointer stores the address of this square. And the stack point, so our stack structure, as you remember maybe from session 4, it will, whenever we push an element, it will reserve 2 spaces, 2 words in this case. One to store the value of the new element, and we will also store a pointer to the next element on the stack. In this case, there's only one element on the stack, so there is no next element, so we put this to 0. Always when we put a pointer to the value 0, we mean to say that this points to nowhere. But we already reserved this memory. It's only when you push the next element that the structure really becomes obvious. So we've pushed now the value 10 to the same stack. And let's look at it again. We have our top pointer right here, pointing now not anymore to the value 5, but to the value 10. Now the address of the value 10 here is address 3, 0, 1, 2, 3. So we have a pointer to the address 3, our new top, and then the next pointer, this field, well, what's the next value on the stack? That's the value 5, so this is pointing to 5. And then the next pointer of 5 is pointing to 0, meaning we've reached the end of the stack. So this is our memory representation of a stack with 2 elements. If we want to traverse the stack, let's say we want to write a function that prints all the elements in the stack, well, then we need to write a function that goes through all of these pointers. So first of all, you dereference the top pointer, which is going to end up here. You're going to find this location. And then if you want to find the next element on the stack, well, you just take this location plus, in this case, 1. And then you go here, and so forth. So you just follow all the pointers, and this way you can traverse the entire stack. This is the memory representation of a dynamic data structure. We've already seen this stuff. This is just repetition. Okay? When we pop another element, the new top now points to the address 1, and then the next pointer is pointing to 0, and that's it basically. That's a simple stack representation. Now let's see how all of this is done in C. So the first thing you're going to do when you want to create a data structure like this in C is you're going to use a struct or multiple structs to define your data structure. Then we're going to use malloc and free, those 2 functions, to allocate space on the heap and free to free space. Let's just give the example of the stack once more. So assume we want to create a stack. What we then do? Well, we have two structs here. Let me first explain. We have our struct stack, which just contains one pointer to a stack element. We just have a second struct for all of the elements. Remember that when we reserve the top, or when we create a new stack, we just reserve one pointer. That's basically, we reserve space to store this struct, and this struct consists of one pointer. To what does this pointer point? To a stack element, which is the current top stack element. When we want to create this, so what we need to do is allocate enough space on the heap to be able to store one pointer. But in general, we want to allocate enough space on the heap to create this struct stack. It's possible that you, for example, store some metadata about a stack in the struct. Let's say you want to name your stack, you could put the name here and other fields. So we don't want to hard code the amount of space we're going to reserve. We have to do that in assembly, but we don't have to do that in C. So what we're going to do is we're going to use size of. Remember from our C exercises, size of gives you the amount of bytes of the data type you provide to it. In this case, we provide the struct stack data structure. The full name of this data structure is struct stack. So we provide struct stack to size of. This will then translate to, on 32-bit RISC-V, this would translate to 4 bytes. It depends on what architecture you're compiling to, of course, what the size is of a pointer. But in our case, for RISC-V, it would be 4 bytes. So this size of operator would resolve to the value 4. And so you're calling malloc with 4, which means allocate 4 bytes of memory. And the return of malloc will be the value, or will be the address of the newly allocated memory. Remember also from session 4, this is nothing new. This is how we wrote our own memory allocator. You call alloc, some allocate function, it returns you an address of the bytes you just allocated. Right? So this is how in C you write this. We've now reserved enough space on the heap to store a struct stack. And then we store this space, or the address of the space, we store that into the struct stack pointer. We call this S. So now we have created a stack. We did the same thing as what is represented here in memory. Well, actually, we do one more thing. We explicitly store the value null there to make sure if this heap memory that we just reserved, if that contains some random garbage values, that we override it with the value 0. And then we have created an empty stack, which is just the top pointer to null. We can return this pointer from this function. That's the return value. And that's how a create stack function would work. It's very simple. You allocate the space, you return the space. Now, how would we translate now a stack push? Let's discuss this struct element structure. So, an element on the stack consists of a value and the address of the next element. So, we've just defined that in our second struct, the struct element. So the struct element contains a value. In this case, we used an integer, which would be 4 bytes on RISC-V. And we've used struct stack element star, so a pointer to the next element. A pointer on RISC-V is 4 bytes, so 8 bytes total for this struct. Of course, remember that it's still possible, again, that your compiler might introduce some padding. In this case, it probably won't, but there is no guarantee that this is actually 8 bytes. Your compiler is free to make this 10 bytes if it wants to. So we use them when we allocate values on the heap, we use size of. Of course, when you are translating to RISC-V, you are the compiler. You are playing the role of the compiler. And so you can choose to use whatever space you want, but it would be logical to... Of course, the minimum is 8 bytes here. But you can allocate more if you want to, but it makes sense to allocate enough, just enough, so 8 bytes in this case. So in any case, when we want to push an element to the stack, first parameter is going to be the pointer S. So the pointer to the struct stack, remember this first square here, is going to be our top pointer, our struct stack. And this square has an address, and that was being stored in S. We call S equals stack create. So the return value here, we store that in S. So S is basically the address of this square in memory, the top pointer. And that's what we use as a representation when we pass around our stack. The pointer to the top pointer. A pointer to the top pointer is basically how we represent our stack. So that's the first parameter to stack push. Second parameter is int val. So the value that we want to push. So what we then do is we first allocate new space, these two new words, to store our integer, to store our next pointer. So this is going to be 8 bytes on RISC-V. What we can then do is we can set the element value here to the provided value. In this case, we pushed 5. So we store 5 in this square. And then we would, well, when we push an element to the stack, this new element is going to be pointing to the old or the next value. The next element on the stack is going to be pointing to the previous stack top. Let's go all the way back here. whenever we push this element now, so currently 5 is pointing to nowhere, the next element is 0, so, but if we push it up, and if we push the next element, then the next value of 10 will be pointing to the previous stack top. That's how a push on a stack works. So that's what we encode here. We say the next element pointer points to the previous stack top. And then we adjust the stack top to point to the newly pushed element. And there we have pushed a value to the stack. Now one note. In our assignment, we've been quite strict. And there is a situation in which malloc can return 0. So malloc can return a null pointer. If you would execute this slide code where malloc returns 0, you would get a null pointer dereference here, and most likely your program will crash. So in the assignment, we are requiring you to actually check. So this is also described in the assignment, to actually check the return value of malloc. This is good practice in C programming. Check that malloc effectively didn't return 0. If malloc returns 0, malloc has failed to allocate your memory and you can't continue with your function. So we have provided you with error codes that you can return from your function in case this happens. I just noticed this star here, by the way, is out of place. It should just be void stack push. There's no star here. This would imply we are returning some pointer. We don't. So this is a stack push function, very simply in C. Notice that we are allocating this time a struct stack element, which is different from a struct stack. Struct stack is just one top pointer. The struct stack element contains a value and a pointer to the next element. We can push with the same code another value to the stack. So now this top pointer would point to 10 again, this next pointer would point to 5, and this would be the end of the stack, the bottom of the stack, the value 5. And then when we look at the pop code, it's also very simple. So we removed an element from the stack. Again, we provide just the pointer S. And when we look here at the implementation, what we need to do when we pop an element from the stack is we need to remove, or we need to let the top pointer of the stack point to the second element of the stack. So that's the next of the top. So how we wrote this here, first, the element that's going to be popped, we store that in a variable called popped. That's just the current top of the stack, because that's what pop does, it removes the top of the stack. So the value we stored is in popval. This is going to be the return value of our function, because stack pop returns the value that was just popped. And then all we need to do is to correct the pointers and to free the memory. Notice that we have more memory reserved here than after the pop. Of course, this value is popped, the top stack value. We need to unreserve that memory by freeing it. So whenever we have pointed our stack top to the second element, so to the next element of the old top, which is the popped value, then we can free this popped value or this popped struct. So we pop these two elements. This is a struct stack element. We remove this, and once all the pointers are correctly initialized, we can free this memory. If you don't free this memory, then we still have a stack with one element, but you also have some memory to which you don't have any pointers anymore. This is going to be memory that cannot be freed in the future, and you have a memory leak. So that's why you always need to free your memory. And then you could just return the pop value as said before. So this is how you use malloc and free in combination with structs to create dynamic data structures in C. This is what you will need to do, but then for the linked list structure. So a linked list could look something like this, where you have a struct list, just like you have the struct stack, where you store the first element of the list, and then each list element could contain a key and could contain a next element. Notice you could perfectly define a linked list to have an array of values here and to link arrays. This is what we explained in the presentation of session 4. You could, for example, say store 10 values and then the next list element. All it means is you're connecting chunks of memory using next pointers. And by this, you create dynamically sized array or a list. But in our assignment, we store one value per list element. And then you could consider a stack to be a special case of a linked list, where you don't store the first element, but you store the last element of the list. And then each element would have a pointer to the previous one, and then you have a stack. But a linked list is the more general dynamic data structure. So linked lists store values as set. The values are stored or linked together through pointers, and the last element will be a null pointer. So you will recognize the last list element by the null pointer. So your challenge is now going to be to figure out how you have to update each pointer. Of course, to allocate these structures on the heap using malloc and free, and then figure out how should you allocate each, or how should you assign each pointer to make sure all of these provided functions from the assignment will work. Now, some general info, and I'm going to give this using the actual files.